Hello everyone, welcome to ECE381 class. In this class, we'll study time-varying fields and Maxwell equations. And based on that, we're going to find out how the electromagnetic wave propagates, including the reflection and transmission of waves at the media interface. Then we'll analyze transmission lines and antennas. If you have not read the course syllabus, please go to the website to read it and find out the important items related to this course, as well as day-by-day class arrangement. At the class meetings, we are going to ask you questions related to the material we are covering. Even though I won't be able to hear your answers, I still want you to think about the questions and try to find out the correct answers. Therefore, I'm going to leave you time for you to think about the questions. And the lectures are grouped in units. Each unit corresponds to one class meeting. Okay. Now let's start from the first unit, Unit 1, which is the first part of Chapter 9 about time-varying fields and Maxwell equations. Recall that in ECE380 we studied electrostatics and magnetostatics. In electrostatics, the first equation is about Gauss' law, which states that the surface integral of the electric flux density D dotted with ds over a closed surface S is equal to Q, which is charge enclosed by the closed surface. As I said, this is a mathematical representation of Gauss' law. The second important equation about electrostatics indicates that the line integral of the electric field intensity E dotted with dl along a closed path L is equal to 0. For magnetostatics, the first important equation indicates that the surface integral of the magnetic flux density B dotted with ds over a closed surface S is equal to 0. And this equation is known as the Gauss law for magnetic field. The second important equation indicates that the line integral over a closed path of the magnetic field intensity H dotted with dl is equal to the total current I enclosed by the closed path. And these two sets of equations are the most important equations governing the static fields. As we know, these two sets of equations are valid when the current and charge Q do not vary with time t. In other words, the current and the charge are both DC, and under these conditions, the current I only produces magnetic field intensity, and charge Q generates the electric field only. And under these conditions, the electric and the magnetic field are not related to each other, and these two sets of equations are separated. However, as we know, in practice, the current may vary with time t, such as an AC current. For such a time-varying current, it will generate both magnetic field and electric field. In addition, the time-varying electric and the magnetic field are coupled to each other. In other words, these two sets of equations are no longer true for time-varying fields, and the equations listed above for static fields must be modified. So in Chapter 9, we're going to find out the behavior of the time-varying fields and how these two sets of equations are modified to Maxwell equations.